Hello friends, in this video we will learn about lateral torsional buckling of a symmetric section. So first we will see what are the reason for lateral torsional buckling in a beam, and this we will illustrate for a simply supported I-beam section. And then we will derive expression for critical moment at which the phenomena of lateral torsional buckling in beam starts. We will also see the effect of various loading and support condition on critical moment. And finally, we will see what are the different provisions that has been provided in Indian standards, that is IS 800 2007, regarding the lateral torsional buckling of a beam. So let's get started. So let us consider a I cross section, and in this case you can see there are two axes, one is Z axis, another is Y axis. The moment of inertia about the Z axis is relatively larger than the moment of inertia about the Y axis. That's why the Z axis is often called as major axis or a strong axis, and the Y axis is called minor axis or the weak axis. And the reason for larger moment about z-axis is because most of the masses are away from the axis, and that contributes more to the moment of inertia. So now let us consider a simply supported I-beam, and a moment of amount m has been applied at both ends of this beam, and the length of the beam is given, that is L. Now what will happen if I increase my moment m? What will happen to the bending of the beam? So the beam will first bend and it will deflect in the vertical direction. But after a certain point of time, if I keep increasing moment m, the beam will laterally deflect, and this phenomena is called lateral torsional buckling. So first beam bends about the strong axis up to a critical load, and then it buckles. So beam buckles about the weak axis even though it has been loaded in the strong plane. So buckling happens about the weak axis because the moment of inertia about the weak axis is smaller compared to the strong axis, and that's why buckling happens about the weak axis even though this member has been loaded in a strong plane. So now the question is, at what point of time, for what moment, that is the what critical moment, this phenomena will start. To find out this critical moment, we will derive a theory, and that theory basically has some assumptions. So let us discuss those assumptions first. So to derive the theory of lateral torsional buckling, the first assumption is the beam is initially undistorted. So there is no distortion in the beam. The second is its behavior is elastic. There is no yielding. So we are dealing with a situation when we have a stress is proportional to a strain. Another assumption is it is loaded by equal and opposite end moment in the plane of wave. As we said earlier, we are applying equal and opposite moment at both sides. In that case, we have a moment m, and this is applied in the plane of wave. And the beam does not have any residual stresses, so we are assuming that there is no residual stresses in the beam across the length. And finally, we are assuming that its ends are simply supported vertically as well as laterally. So there are two kinds of restraint that is simply supported in case of vertical direction as well as in case of lateral direction. So using this assumption, we can derive theory for lateral torsional buckling. And we can also find expression for critical moment. So let us consider this beam. So we have a I beam and length of the beam is L, and this beam has been applied by a moment m. So we are applying a moment m at both ends of this beam. Now this beam will basically deflect. So if you see this beam under the bending action, the bottom flange will be in tension and the top flange will be in compression. So the whole top flange is under compression. So if you remember the compression member, so if we apply a force on a compression on any slender member, it buckles. So same phenomenon will also happen in this case. So my whole flange is under compression. This means if I increase my compressive force, a point will come, this will buckle. And there are two possibilities. It can either buckle in vertical direction or it can buckle in lateral direction. But in the vertical direction, due to this beam, it cannot buckle because there is a restraint in the vertical direction. So there is only one possibility, that it will buckle in horizontal direction or it will show horizontal deflection. Something like this. So this is the horizontal deflection that we have in this case. But you see in this case, the tension member, that is the bottom flange, is not trying to buckle. That tries to remain at its own position. So that's why the whole section basically rotates. So you see this section has rotated by some amount. So the top flange wants to deflect, but the bottom flange doesn't want to deflect. As a result, this cross section basically twists. Moreover, the beam will also deflect in the vertical direction. So this is the deflection in the vertical direction, and this will occur because of the bending of this section. So if we consider any cross section, for example, if I consider a cross section here, and then we can show the deflected shape. So this is the deflected shape at this cross section. So this shows this has rotated by angle phi, that is a twisting action, and it has laterally deflected by an amount u, and this has also deflected in the vertical direction. Now if we consider the equilibrium of this cross section, we can basically write a differential equation. And this is the differential equation for this phenomena. In this case, this is a fourth order differential equation, and we have term EIW, ZIT and EIY. These terms basically denotes the different types of resistance or different types of rigidity provided by the beam. So this is the same expression, and these are the terms. So EIY, that is basically flexural rigidity about the minor axis, that is y-axis, and ZIT is the torsional rigidity, that is it tries to prevent the torsion, and EIW is warping rigidity, it basically tries to prevent the warping of the flange. Now we can solve this differential equation and we can find the critical moment. And this is very similar to the compression member. So if you remember, if you have a compression member and if you apply a force P, then up to certain point of time, this compression members buckle, and you can find the critical force at which the compression member buckles. Similarly, in this case also, you are increasing M, you can find a moment M at the point of time this member is going to laterally buckle. So finding expression for critical bending moment at which lateral torsional buckling occurs is very similar to finding the force or critical force at which buckling in a compression member occurs. So this is the critical moment at which we will have lateral torsional buckling. Basically this is coming from the solution of this differential equation. Now if you see this expression, basically there are two terms, this one and this one. So the first term is related to EIY and ZIT. So the first term is related to flexural rigidity and ZIT, that is torsional rigidity. And the second term is related to warping rigidity. So we can show the same critical moment expression. So there are two terms, one is this one, another is this one, and the first term is related to torsional resistance, another term is related to warping resistance. Basically we can write M critical is equals to under root of torsional resistance whole square plus warping resistance whole square. So if you take root of this term, that is related to torsional resistance, and if you take root of this term, this is related to warping resistance of the flange section. So this term, that is torsional resistance, is the capacity of beam shaped to resist shunt, bend and torsion. And the second term basically measure of warping contribution to the torsional resistance of the beam. We can also rewrite the expression for critical moment. So if I take pi square L square outside of the root, and we can also take EIY and ZIT that is outside of the root, so that the first term become 1, and then we can rewrite the expression for critical moment. So let's rewrite. So let's take pi square L square EIY ZIT outside of the root. So if I take this term outside of the root, we will have pi by L, and this will come outside as a root, and we will have 1 plus this term. So this is the modified expression we will have for critical bending moment at which lateral torsional buckling will occur. So basically this derivation makes many assumptions which may not be realized in practice. For example, the beam is assumed to be initially undistorted without any imperfection, which is not often the case. The beam, so if you are transporting a beam from one place to another place, it often gets distorted, and also it has some kind of imperfection. We cannot produce a beam without imperfection even in the rolling mill. And the behavior of beam is elastic. So we often go into the inelastic range. So my forces or loads are higher, or due to some reason we have inelastic range. So this assumption is often violated. The beam is loaded by equal and opposite end moment. So we can have different moment. One side we have another moment, on the other side we have different moments. So not always equal. And it is assumed that the moments are applied in the plane of wave. This is not the case. We cannot have always moment in the plane of wave. So it goes out of the plane of the wave. So this basically all avoids or violates the assumption that has been made in this theory. Some more assumption that gets violated, for example, ends of the beam are simply supported vertically as well as laterally. So we can't have always simple supported in vertical and lateral direction. The beam does not have residual stresses, though these are invariably there. So we have residual stresses inside the beam. So basically we are avoiding this assumption of the theory for lateral torsional buckling. So this is the expression for critical moment that will cause lateral torsional buckling in the beam. One important point in this expression, we have length, and this length is unbrushed length. So this equation is applicable only if moment is uniform over the unbrushed length of the beam. So we having an assumption that my moment is uniform over the unbrushed length of the beam. So basically this theory makes many assumptions that often gets violated. For example, moment is not always uniform. It can have a different kind of distribution of the moment. So we have to account for all this kind of imperfection or violation of the assumption, and we need to modify the expression for critical moment for lateral torsional buckling. So how we do that? Basically, Indian standards, that is IS 800 2007, provides different constants or multiply by different constants to account all these effects. For example, to account for the different loading and support condition, it takes a constant C1 and it multiplied the critical moment expression to get the revised critical moment. So now if you see this expression, C1 is a constant, we can also find another constant, that this term is a constant and this pi by L is a constant. So if I multiply pi by L with this term, I can write something like this. So pi by L and this term. So this is a constant. Let's put this constant as gamma. So in terms of gamma and C1, the expression for critical moment is very simplified, and this can be written by this. Now we will see what are the significance of different terms that we have in this expression for critical moment. So let us discuss first C1. So the term C1. Basically, the term C1 accounts for the different kinds of moment distribution. My theory assumes that we have a uniform moment, but we will always have different kind of moment. So what we do in that case, we multiply by a constant C1 to get the equivalent uniform moment. So this says a loading condition other than uniform moment can be represented as an equivalent uniform moment multiplied with a numerical equivalency factor. So if I have a non-uniform moment, then we have to multiply by a constant C1 to get a equivalent uniform moment. This factor accounts for the effect of differential moment gradient on lateral torsional buckling. So we have a moment gradient, and to account for this moment gradient on lateral torsional buckling, we have to consider a term C1 in the lateral torsional buckling critical moment expression. To take into account the non-uniform bending, a modifier C1 called equivalent uniform moment factor or moment coefficient is used. So basically, this factor is called moment coefficient or equivalent uniform moment factor that is used to account for the non-uniform moment behavior or moment gradient behavior into the critical moment expression. And this is given in IS 800 2007. So if you see table 42 of this code, you will find for different bending moment diagrams. So these are the different bending moment diagram. You have a constant C. So you see in all cases, so if you have a uniform bending moment, this value is 1. But for other cases, you have a value of C1 that is larger than 1. So we have illustrated the effect of C1 in MCR expression. Now let us discuss the other term, that is a square root of E sub I by and Gi sub T. So this term is related to shape and material of the beam. So you see E, I, so these terms are basically related to material. So E and Z is related to material of the beam, and I by and IT is related to the shape of the beam. So with increase in this term, MCR value increases. That is, if you increase either E, I by or ZIT, because this term is multiplied in MCR expression, so basically your critical moment also increases if you increase any one of this term. Now sections with greater lateral bending I by and torsional stiffness IT have great resistance to bending. So this means if you increase I by and IT, the MCR value will increase. In other words, resistance towards lateral torsional buckling or resistance towards lateral buckling will increase. And now I have a question at this point. What do you think about this term, that is this term, for I section? So this will be large or this will be a small. So if you remember in I section, as I discussed earlier, the IY value is very small and IT value is also very small, and that's why we can say this term will have a smaller value. This means the I section is not enough or not good for providing resistance towards lateral torsional buckling. So basically, I section with large in plane bending stiffness does not has lateral stability. It is because I section have high major axis bending strength compared to the minor axis bending as well as twisting. So as I was saying, the IY value and IT value for I section is small, and that's why it is not good for lateral stability. So now we have discussed two terms in MCR expression. First is C1, another is the square root of EIYZIT, and the next term we have, that is gamma, that is the third term. This is the term gamma, that is a constant, and this varies with the length of the beam. So you see in this expression we have length, so the gamma depends upon the length of the beam. So for beam with no intermediate lateral restraint, the effective length, that is L, is equals to the actual length between the supports. So if we provide no such kind of lateral restraint, the effective length is simply equals to the length between the support. If such a support is provided at the midspan, so this means we are providing some support, let's say at midspan, the beam span is halved and each span will be halved independently. So if we are providing a lateral support, let's say in the mid, then we will have half of the length, that is L by 2, and these two parts will be halved independently. And the next is the warping resistance at the support or at breast point may be represented by the effective length factor K. So we are introducing another factor, that is K, that is effective length factor wherever we have the breast point or we are providing a warping resistance, let's say at support. So this effective length factor, that is the K, is used to describe rotational freedom about the vertical axis, that is warping, at support or the breast point. So we are introducing a factor K, and this factor basically denotes or describes the rotational freedom about the vertical axis at the support or the breast point, and which is related to the warping action. For example, if the flanges are not restrained against warping, we will put K equals to 1. And for the flanges restrained fully, theoretically we will have K is equals to 0.5. But the IS code takes a value of 0.7 for the design purposes. So what we are saying is, we are saying we will have different value of K depending upon the restraint provided at the support or the breast point. So if we have no restraint against warping, let's put K is equals to 1, and if we have restraint against warping, we will take value of 0.7 that is provided in IS 800. The effective length of beam subjected to lateral torsional buckling have also been denoted by L sub LT. So we will use this term where LT denotes lateral. So this is lateral torsional buckling. And the value of effective lateral length, that is L sub LT, is given in IS 800 2007. For example, clause 8.3 of the code says effective length for lateral torsional buckling for simply supported beams and girders of a span length L. So this is for simply supported. So we have two clauses, one for simply supported, another for cantilever beam, and for these two we have been given two tables. So that is code provide you the two tables. So for simply supported beams and girders of a span length L, where no lateral restraint to the compression flanges is provided, but where each end of the beam is restrained against torsion, the effective length L sub LT of the lateral buckling to be used in clause 8.2.2.1 and shall be taken as in table 15. So we have been given this value in table 15. Similarly, for cantilever beam, this is given in table 16 and this is illustrated in clause 8.3.3. So this is table 15 of the code. So this gives effective length of simply supported beam, and there are two conditions. One is torsional restraint, another is warping restraint. For example, if torsional restraint, that is the fully restrained, and the warping restraint, that is both flanges are fully restrained, in case of normal loading we will have a value of 0.7 L, and if we have a destabilizing loading, in that case we will have a value of 0.85 L. Similarly, table 15 of this code gives effective length for cantilever beam. So this is basically 16. So this gives effective length for cantilever of length L. So this gives the restraint condition at support and at the top. So if I have a continuous support with lateral restraint at top flange and at the top it is free, then for the normal loading condition the effective length is 3L, and for destabilizing condition the effective length is 7.5 L. And the two loading condition, that is stabilizing and destabilizing, that we discussed earlier in the previous slide. So this is a stabilizing, that is this tries to apply a moment so that the deflected member or deflected cross section or deflected beam comes into the original shape. However, this is a case of destabilizing loading condition. In this case, this load is trying to deflect further to the beam, so that this is a destabilizing loading condition. So we have seen the effect or significance of three terms in MCR expression. Basically, IS 800 also gives an expression for critical moment for lateral torsional buckling. So this is the expression for MCR that is given in clause 8.3 of the code. Now this expression, this is elastic lateral torsional buckling moment in case of simply supported prismatic members with symmetric cross section. The elastic lateral torsional buckling moment M sub CR can be determined from this expression. Now this expression is same as the previous expression that we derived, but little bit in a modified form. So this is same as, but the terms has been rearranged. So this is the expression that we derived. So now if I take pi s square EI by divided by L square, that is this term outside, or take common, so we will have this expression. So if I take this term common, I will be left with this term, and this term is same as this term. Only thing is, in place of L square we have effective length, that is L and L sub LT. So where L sub LT basically denotes the effective length against lateral torsional buckling. So in this video we have seen how to derive expression for critical moment, that is critical moment for lateral torsional buckling, and what are the significance of different terms that occurs in MCR expression, and what are the provisions that has been given in IS 800 2007. So thank you for watching this video, and we'll see you in the next video. Thank you.